So we're going to continue our exploration of producer theory today and talk about a few new concepts or additional concepts that we haven't covered yet. So the last time we talked about returns to scale, we talked about homogeneous functions of degree k and of degree 1, in particular for constant returns to scale. We talked about what that feature of these functions does for the marginal products of labor and capital. Because that's the feature of both of the marginal products, that means that the MRTS, the marginal rate of technical substitution, is going to be the same across the array from the origin. So if you think about a firm expanding labor and capital proportionally, let's say you have a 2-to-1 ratio and you grow, you double capital and labor proportionally, that marginal rate of technical substitution is going to be the same. So we're going to push these concepts a little bit further. So today I'm going to be talking about elasticity of substitution and how useful it is for analysis in microeconomics. And then the last part for production theory has to do with looking at a few examples of production functions. And I'll go through some of them, and some of them you're going to be thinking about in your problem sets, in your homework. So I'm going to start and begin with the concept of the elasticity of substitution. That is denoted as sigma. You're going to see the symbol usually. It's like an O with a hat going towards the right. That's the Greek letter. Just for Greek side lesson in microeconomics, this is the capital sigma. We use that for the symbol for the sum, right? That's where you've seen that. There's another version of a sigma in Greek. It looks very much like the S symbol. So that's a big parenthesis over here. What does it measure? The elasticity of substitution. It measures the proportionate change in the capital to labor ratio relative to the proportionate change in the MRT along an isoquant. So that's a big sentence. So I'm going to write it down mathematically first. So I'm going to say that sigma is equal to percent change in the capital to labor ratio as the percent as you change the MRTS by a small percentage point. So it is associating what is happening to your capital to labor ratio, whether you have a capital-intensive production or a labor-intensive production process, to the changes in the marginal rate of technical substitution, okay, as you're moving effectively along an isoquant, keeping quantities the same. And that's going to be effectively a measure of how easy it is to substitute one input for another input. That's something that in econometrics people go and try to estimate directly, right? So I'm going to write it in the form of a sentence too. So I'm going to say measures the proportionate change in the capital to labor ratio relative to the proportionate change in the MRTS, labor for capital, along an isoquant. Some points here, sort of conceptually. What do we expect the sign of that thing to be? Okay, and I'll show you a picture. How about, so if you have, let's say, our standard diagram where we plot the space of our inputs. Let's put it this way. 2 inputs, capital and labor, and we plot this isoquant here. How does MRTS and the capital to labor ratio change? For example, let's go with the story of a diminishing marginal rate of technical substitution. Let's say if you're moving from here to here, right? So you have this MRTS over here being this slope, right? What has happened to the slope? It dropped, right? So the MRT diminishes, right? So you have a flatter slope at the second point as you move in this direction, right? So the MRTS effectively drops because it's measured by the slope of the isoquant, right? So MRTS drops. What happens to the capital to labor ratio as you're moving across the 2 points?
It's smaller.
the capital to labor ratio gets smaller, right? Of course, you become sort of more labor intensive versus capital intensive. So we expect, because these two things move in the same direction, there's a co-movement, we expect that sigma to be positive. So I'm going to say here, if what happens is capital to labor ratio falls, I'm going to say from A to B, capital to labor ratio falls and MRT diminishes. Okay, so expect then sigma be positive, right? Because it's an elasticity measure. You understand that, right? So that your standard price elasticity measurement is a negative number because you have a negative association between price and quantity, right? So an elasticity measure is because you increase this, so that's a negative sign. This one is because you have a movement same direction. This becomes smaller. We expect capital to labor ratio to drop, positive sign. This increases capital to labor ratio, also increases that percentage ratio going to have a positive sign. Okay, that's sort of our for how this is going to work. Other note, or intuitively, sigma is an indicator that to how it is to substitute one input for another. I'm sorry, you can tell me if I forget to erase the paper. Okay, of math, I'm going to say mathematically. So we said that sigma is that percent change I can push this definition. You have seen something similar when you've discussed elasticity in the past, where you can go from this expression to sort of this. So how can I write this as a percent change using derivatives?
Derivative of the natural log of Kano?
Eventually, we're going to get to this expression, right? So you can express this as del ln of k over L, del ln of MRTS. And you've probably worked on something similar in the past, and you know that sort of derivation. But let me do it really quickly here. So the percent change in capital over labor, we can usually express as the change in capital over labor over the variable itself, right? So that would be your change. So it's dx over x, right? Does that make sense as a percent change? How much did you change x over the value of x, right? Let's say the original value of x. And the same for the percent change of MRTS. You can write this as d of the MRTS divided by MRTS itself. What is this going to be equal to? So we can pull these in the denominator, these two on the numerator at the outside, these on the denominator. So you can form an expression that the sort of the derivative components that on the one side, del MRTS here, and then multiply that with MRTS by K over L. Okay, so you see how I did that simplification of the more complex ratio. Okay, and here you can work your sort of definition of the ln x, the natural logarithm of x. So if you remember ln of x dx, do you remember what is our formula from calculus? 1 over x. Very good. Okay, which I can rewrite this, right? I can here to say that this is dln of x is equal to dx over x, right? And this is effectively why we result, right? It's based on the fact that we can express the as of the variable. So if you apply this to this expression, let's see what happens. You have the dk over dk divided L, and you have the k over L. These two things are going to give us the of k over L. And then over here, you have something similar, the DMRTS and the MR itself, but it are in reverse places, right? It's saying it's 1 over DMRTS over, so that's why we put the DLN of MRTS down here, okay? And complete sort of this. So that's on the measurement side of things. Elasticity substitution also ranges from infinity to 0, infinity. Okay. Okay. So, a few other notes about this concept. If PS does not change much for in K over L, substitution is easy. On the other hand, if the MRTS does change rapidly for capital over labor, substitution is difficult. Okay, so why all of this happening, right? So you have this because, let's say, minor in K over L. That is effectively that's your mix. That's another way of expressing this. Sort of the relative sort of use of the inputs. Significantly affect the input relative productivity. So that's for the second point over here, right? So think about this as the easiest way to conceptualize this without, we're going to draw the diagram too, but without drawing the diagram is the following. You have small variations in your capital to labor ratio. That means you're changing the mix a little bit, right? You make small adjustments, either you hire a little bit of labor, you drop your capital intensiveness by a little bit, right? So you make these small adjustments, and then you see a significant effect, the input relative productivity, which is expressed by the MRTS, the ratio of the marginal products. If the sort of is a significant effect, then the substitution is the right. So it relates the quantities of your inputs to their relative productivity. If you want to boil it down to a simple sentence, because think about it, right? So each of these inputs has a marginal productivity, right? Especially if you're not moving a long array in a predefined sort of production function, that's going to have an effect on the marginal productivity of the inputs, right? So how you're changing your capital to labor mix is going to have an effect on the productivity of the ratio, which is effectively the rate of technical substitution, right? So that's the whole point. I mean, the substitution tries to capture what is happening on level. Let me draw the diagram here too. So diagrammatically, you have capital over here, you have labor over here, standard stuff, and you are producing a quantity called Q bar. This is a point that we can call A. This is a point that we can call B down here, right? So the array from the 2A is going to give you, or if you look at this as an angle, this is your capital to labor ratio for point A. Does that make sense? Right? If the angle is big, you have a high capital to labor ratio. If that angle is small, you have a small capital to labor ratio. Can you both see what I wrote? Yeah, it's a vertical line and the subscript of A, just to denote that this is the capital to labor ratio for point A. Yeah. You draw the to point B. That's the angle over here, right? Obviously, a smaller angle than the one. That is the capital to labor ratio for point B. Okay, so we're going to, so if you think about movement from A to B, right? Movement, which is an exaggerated motion, right? We typically think about like a marginal or a percent, depends on sort of the movement from A to B. Does the labor ratio change? We're still producing Q bar, but our capital to labor ratio is different. Has the MRTS changed? Remember how we measure the MRTS on a point of a slope of the isoquant? It has changed, right? It has dropped. It used to be a high slope, and now a much flatter slope. Okay, so just here, both the MRTS and the capital to labor ratio has changed. Okay, how is TS measured? So here is the MRT slope, effectively. This is the slope for point B, sort of the line that is tangent to the isoquants, right? High slope for point A, okay. Low MRTS for point B. So sigma is simply a ratio of these changes as an elasticity measure, which means as a percent change measurement, right? So sigma is the ratio of these changes as an elasticity measure. So how did the relative marginal productivity of these inputs change as you're changing the relative mix of the inputs in the production process? Does that concept sort of make sense, right? Going back to the definition of what is the marginal rate of technical substitution. It's a ratio of two marginal products. So that is the relative productivity of the two inputs. So how does the relative productivity of the two inputs change as you're changing the input mix, which is the relative labor capital relative, right? So the sigma simply measures that sort of responsiveness of the relative productivity of the inputs to the relative mix of the inputs. That's all that is, and it's forming it as an elasticity, which means a percent change of one has this percent change on the other. That's all that it is. So it might look a little bit fancy, but it's, you wanna in sort of in a sentence, if you will. Okay. So sigma curvature of the isoquant. That would be another way of thinking of, right? So does that make somewhat of a sense how we associate relative productivities of inputs to the actual of inputs that we're using in the production process? Because if you start reducing an input, you lose, or you might be increasing sort of the marginal productivity as you're changing the mix, right? So that has implications for the production in terms of what is possible effectively. So let's look at these curves in an additional. Let's look at the case of a high elasticity of substitution. So here the MRTS does not change substantially relative to the K to the capital to labor ratio. So the isoquant is relatively flat. So I'm going to draw this so you can see how that works. So you have maybe an isoquant that looks like this. You have point A here, point B here. The ray from the origin to A shows you the labor ratio for point A for that particular input mix, right? This one is a smaller slope, smaller K12 for point B. And you see that the MRTS in this situation does not change substantially. So the marginal productivity is effectively, the ratio of the marginal productivities is not going to be very different. So that shows a high elasticity of substitution. Substitution is effectively easy because by changing the input mix, you're not affecting the marginal productivities of those inputs. Okay, in percent terms. How about a low elasticity of substitution?
Question with the high elasticity.
Yeah.
That high talks about linear,
Yeah.
but so linear is like infinite, and you can have any slope of your line to
Correct.
to have a high elasticity. I'm just trying to conceptualize.
Yeah, because the change, effectively no change in the marginal rate of technical substitution when the production function is linear, correct? Because you're measuring the isoquant, and in a straight line, if that's your isoquant, the slope is never going to change. So change your capital to labor ratio all you want, the marginal rate of substitution is not going to change. Correct. It's going to be constant along the lines. This is a very similar example, right? In this situation, it changes, but little, right? So this example, the next one, sorry, I should have measured the average. This example over here is going to show you the low elasticity. So I should have said over here the MRTS changes substantially relative to K over L. The isoquant is sharply curved. So you would have like a higher degree of curvature. You see that? So if you were going to go from here, from point A to point B, okay, here is the in capital to labor ratio. This is the capital to labor ratio. Point B, okay. Look at this for point A, very, very high. Look at the slope at B, relatively flat slope, right? So the MRTS has changed substantially relative to the capital to labor ratio in this particular example. Okay, graph paper helps all of these. Okay, so a note that connects this to actual data. Sigma is across industrial sectors. Some folks estimated, there are econometric studies out there that are trying to capture this unbiased estimate of what that is, all these methods that you have been exposed to through regression analysis, right? Perhaps more recently using fancier techniques like the learning in advanced econometrics. But I'm going to give you some numbers been produced relatively recently. So estimated sigmas, a different production function that you may know can shift effectively. CES production function. So from a CES production function that is paper from in 1998, and it's about Germany. Here's the analyst industry and the that was estimated. So you have also in descending order of sigma. You have food having a sigma of 0.66, iron having a sigma of 0.50, chemicals at 0.37, and vehicles at 0.10. Okay. Interpretation. How would you try to put this into words?
You swap labor and capital when making food and motor vehicles.
Right. Given the sort of the effects on the marginal productivity that labor has in each of these sectors. Okay. Yeah.
Is that more like for food, for making bread versus smelting iron versus making chemicals versus specialized machinery required to make motor vehicles? That's essentially what we talked about. That's that.
Right. It might be the sort of the actual capital that is being used, and what is to change labor for the operation of that type of capital, for example. Yeah. Okay. You'll see how that use that concept as we go along. When we talked about market structures, it comes into play later. But at this point, we're simply trying to describe a firm's technology, assuming, so for particular cases, that each of these firms in the food industry are similar, right? So for a representative firm in that industry, for example. Okay. A last note, elasticity of substitution. Note here, sigma can be or decreasing with scale, rather with. So I'm going to draw this. So what we're talking about is the curvature of the isoquants. The curvature of the isoquants could be increasing or decreasing as you're adding to production or removing portions of the production, right? So you could have in this picture over here, sigma decreasing with scale. Okay. By saying with, we mean that we're going to be looking at multiple isoquants, different levels of production. Sigma decreasing means it becomes more curved rather than flat all over, right? So let's say you start with a linear isoquant, and as you increase that, it starts to become a little bit, pick up some curve. Okay, so capital over here, labor over here. And then we have the alternative situation where sigma could be increasing with scale. Right, so, and I mean, to measure this, you obviously have our firms, and so you can have that as a very analysis. So let's see, you could have that looks like this. So, and then progressively could become flatter. Okay, so I should put something over here that denotes output: Q1, Q0, Q1, Q2, Q3, Q4, here Q1, Q2, Q3. I didn't have a Q0. I don't know what would be the Q0. It was like fixed inputs, sort of technology, moving into something that's much flatter, right? With Q4 greater than Q3, greater than Q2, greater than Q1, greater than Q0. Okay. So that's the idea of how that elasticity of substitution can change as production. The level essentially changes. The scale of production actually changes. Okay. And these are, you can also measure econometrically by controlling for sort of the size of the firm. Okay, so that's theoretically that I have to say about the concept of the elasticity of substitution. So now we can see specific production functions, right, that you have been sort of exposed to before, because we're very similar functional forms in consumer theory, which is kind of funny, right? If you want to think about microeconomic theory more broadly, that a lot of the similar techniques apply to consumers and firms, right? So if you don't have an awareness of what's happening, you could be sort of confused about why economists are thinking like this, but effectively it's because of the sort of economics, right? Trying to describe the world, and we have figured out that we can describe sort of preferences and by using sort of similar mathematicals, and they adopt different meanings as we're thinking about consumers and producers. Okay. So I'm going to say here a few examples. So let's see. First of all, example 1, linear production functions. Form Q is equal to F of K, comma L equals generally to alpha times K plus beta times L. So you can do automatically 3 things for any production function, right? What are the scale for this functional form? How do these isoquants look like? And what is the elasticity of substitution for this production function, right? That's kind of like the, if you will, of each production functions. Let's look at the scale first. You have F of TK, comma TL. Okay, and we're trying to associate that to the original level of production, right? So if F of K, comma L is what we were producing before we increased our capital to T times K, let's say 2 times K, and T times L, 2 times L, for example. Can we associate with the original formulation? A alpha times K plus beta times L. How do you do that? Well, you simply bring this into the picture. So you're going to have into the picture, right? So you have alpha, and in a parenthesis, the new amount of capital. which is T times K, plus beta, we're following the production function. How much labor do we have now? We have T times L. Fantastic. From math that you learned a very long time ago, I believe you can pull the T outside as a common factor here. And you have alpha times K plus beta times L. You tend to forget that math, obviously. T times the original production function, right? So what does this mean? We have found that f of tk tl to t to the power of 1, obviously, times f, the reduction function, f of k comma l. So we have what returns to scale. Okay, fantastic. Call that. How about isoquants? So typically, when we want to draw the isoquants in the two-input case, you think about the space in which the isoquants live. Right? The isoquants live in a space that we have called KL, the KL space, the capital labor space. So if you draw that, capital is on the horizontal line, on the vertical, labor is on the horizontal line. So effectively, in order to draw an isoquant, we want to develop a function of K with respect to L, right? Because that's essentially what it's like when you have like this. You're effectively trying to plot something in here. It's like having an f of x and an x. So vary x a little bit. How does f of x relate to that? Same thing here. If you want to draw something that lives in this space, we'll see that there's another line that we're going to plot in there. That's called the isocost line. Similarly to consumer theory, where you had indifference curves and budget lines. But in order to plot something in here, we have to deal this mathematically. We have to deal with these two variables as if this was the f of x and as if this was the x. That's what we're solving for k. So when I say here, take this q is equal to this and solve for k and make q fixed, and that's going to give you your isoquant. That's all I'm saying. Essentially, develop an f of x as a function of x. Develop a k function effectively as a function of L. So that's what we're doing. So I would say solve for k. And at this time, keep q constant. So first, second. And that should give us an isoquant. So if we say, okay, we want to keep constant, how do we keep q constant? We put a bar on that. So that's like having a number. It's like having an equation where this is a 10. It's not a variable anymore. It's like 100. Is equal to alpha times k plus beta times L. Okay? Solve for k. Easy. Alpha times k is equal to q minus beta times L. Divide both sides alpha, assuming that alpha is different than 0, and you have is equal to q bar divided by alpha minus beta over alpha times L. Okay, that means if you look at this line, it has an intercept and it also has a slope. So I'm going to say this is the intercept. Visible again. So this is the slope. Okay. So a straight for the slope is not changing, correct? So the slope of the isoquant is a constant. Okay. Once you put those down, it's going to be constant. If you want, you can draw this, right? We know how to draw straight lines once we have an intercept. Slope L here, K here, and it's a positive intercept, negative slope. It's going to look something like this. What's going to be the value of the intercept? That is going to be q divided by alpha, and the slope here is going to be minus beta divided by alpha. Does that make sense for everyone? Which brings us, okay, so we did returns to scale. Okay, which brings us to the question of, well, what is the elasticity of substitution for this function? Okay, and that's what we're going to do next. You should already have a sort of that's from read things in your chapter, or generally having that understanding now of how the elasticity of substitution works. So I'm going to say here elasticity of substitution defined as sigma to formally the percent change in the capital to labor ratio as a percent change of the MRTS, which we call infinity in this example because MRTS here is equal to 0. The percent in MRTS is equal to 0 because MRTS is constant, equal to minus beta over alpha. Hopefully that's clear. High elasticity of substitution because you're not affecting, as you're changing the mix of your capital and labor, you're not affecting the relative marginal productivity of the inputs that you're using in the production process.
And so in the book, they essentially just go straight to putting the marginal production of capital over marginal production of labor and giving the slope of the line that way.
Yeah, because that's effectively how MRTS is being calculated. But here you also have it because you have found the functional form of the isoquant and it's not changing, right? It becomes like you don't have a yes. So yes, then minus beta over alpha, you can equate it to the ratio of the marginal products, if you will, right? You know this. You know what is by having sort of identified a linear production function. Okay? Okay. Another example we can is, let's see. I'm going to talk about the fixed proportions production functions. And in this particular example, there is substitution. You always operate on the kink, and the capital to labor ratio is constant. So if you visualize this, capital labor space, the isoquant lives in there, and the form of this isoquant is L-shaped. So you have your capital to labor ratio here, and so on and so forth. If you want to think about what the isoquant looks like, alpha times k equal to beta times L. So k effectively is equal to beta over alpha L at the kink. This effectively means that in order to produce Q1, you need a specific amount of capital and labor, a specific sort of ratio between those two. And if you labor and keep the same, if you're down here, for example, you're still going to be producing Q1. If you increase capital and keep the labor the same, you're still producing Q1. The only way to increase production is to increase both of inputs at the rate at which you're effectively in your production technology. So the other thing is that your sigma here is equal to 0 because the change capital over labor equal to 0. So the numerator is 0. So sigma is equal to 0. There's no other ratio of capital and labor that's going to be used in a fixed production technology. Okay, so that's all the first two examples, and then the next one I believe we're going to look at the Cobb-Douglas production function and maybe the CES, and then we're done with technology side. We're going to start bringing in cost in the consideration here. Okay, that's all.